Welcome. In this movie, we'll look at how to prove some trigonometric limits using some geometry. So here I have a unit circle and an angle theta, and I'm illustrating three regions that we're going to compare their area. So I've got a triangle that goes from the origin out to the point at 1, 0, and then to the point at my angle theta. So this gives me a triangle. Notice that its base is 1, and its height will be the sine of theta. I've got an arc, so a segment of the circle, so I go out to 1, and I go to the angle, and so I get a fraction of a circle, and notice that that's always bigger than the triangle I started with. And then I have a third triangle that goes out to the height, out to the value 1, but instead of going back to the point, it goes vertically until it reaches the same line as the angle theta. It turns out this height is the tangent of theta. So notice this relationship between the triangles and the sector of the circle. The triangle with the height tangent is always bigger than the sector, and the sector is always bigger than the triangle that goes with the chord. So if I think about the shape of these three regions that we've talked about, let's calculate their areas. First, the triangle that's inside, we saw that it had a base of 1 and a height of the sine theta, and so its area is 1/2 of 1 times sine theta, or sine theta over 2. The sector is a fraction of the circle, so I can decide what fraction that is by taking the angle theta and dividing it by the total radians in an entire circle, which is 2 pi. So my sector has a fraction theta over 2 pi of the entire area of a circle. The area of a circle is pi r squared, and the unit circle has radius 1. Consequently, the area of the sector is the angle theta in radians divided by 2. Finally, the triangle outside we saw had a base of 1 and a height of tangent theta, and so when I simplify that, the area equals the sine of theta over 2 times cosine theta. Because of the ordering of the areas, we see that this area of the small triangle is always less than the area of the sector, is always less than the area of the larger triangle, giving me an inequality involving sine theta and the angle theta. If I multiply each term by 2 and divide by sine theta, I get an inequality that 1 is always less than theta over sine theta, which is less than 1 over cosine theta for any positive or negative angle. An important theorem in calculus is something called the sandwich theorem or the squeeze theorem. And it says if I have three functions and the g of x function in this inequality is always between f of x and h of x, and that has to be true for all x values just to the left and the right of my point. And I also know that the limit of the first function f of x and the limit of the last function h of x are both equal to the same value, then the limit of the function inside also equals that limit. So let's take the inequality that we had. We know that 1 is less than theta over sine theta is less than 1 over cosine theta. So if I take the function on the left, it's a constant function. And so the limit of 1 is 1. And then if I look at the function on the right, 1 over cosine theta, we know that the limit of cosine theta is 1 because cosine is continuous. And so the quotient rule says that the limit of 1 over cosine theta also equals 1. So the limit on the left and the limit on the right, the bounding functions, both have a limit of 1. This tells me that the function in the middle, theta over sine theta, has a limit of 1. Well, again, using the quotient rule for limits, I know that that means the reciprocal, the limit of sine theta over theta, is 1. This is one of our fundamental limits in trigonometry. So I know the limit of sine theta over theta is 1. We just proved that using some comparison of areas. And now I want to look at another limit, 1 minus cosine theta over theta. We can't divide by 0, so we can't just put theta equals 0 in our formula. And we remember that we have the Pythagorean identity. Sine squared plus cosine squared of an angle always equals 1. What that means is my cosine of theta is related to the square root of something. is the square root plus or minus the square root of 1 minus sine squared theta. This suggests that we mimic our process of using limits using conjugates. Sorry about the typo. So if I take the limit of 1 minus cosine theta over theta, and I think about what's the conjugate, it's 1 plus cosine theta. So I'll multiply top and bottom by 1 plus cosine theta, expand the top, that'll be 1 minus cosine squared theta. By the Pythagorean identity, 1 minus cosine squared theta is sine squared theta. Now, we need to use our original limit. We know the sine theta over theta has a limit of 1, and our formula has sine squared theta over theta. So let's divide by theta and multiply by theta. And so on the left I get sine squared theta over theta squared, and on the right I get theta over 1 plus cosine theta. The limit on the left, sine squared theta over theta squared, is the square of my original limit. And the function on the right is continuous at 0. So I get 1 squared from the sine squared theta over theta squared, and then times 0 over 1 plus cosine of 0, and cosine of 0 is 1. That simplifies to 0. So I know my second limit. 1 minus cosine theta over theta, as theta goes to 0, approaches the number 0. In calculus, we usually want to think about the limit that's in the opposite order, cosine theta minus 1 over theta, because that will be the derivative of cosine at x equals 0, or at the angle 0. So that's how I can use some geometry to help me calculate some limits.